Okay, everybody, welcome back. So last time we spent time trying to bring some of the background for nonlinear dynamics into your life. We just talked a lot about a pendulum, but we tried to use general ideas about phase portraits, graphical analysis, stability of fixed points, different definitions for stability, how nonlinear systems can do crazy things like have fixed points that move around and bifurcate and do all kinds of crazy things. That was the sort of crash course. But what I left with at the end, right, was sort of a challenge, which was that you're given a vector field, which you can think about graphically, and now you have some control authority. And my challenge was, how do you design a controller that changes the vector field just a little bit and tries to accomplish the goals you want? Moving the fixed points, changing the stability properties, making it do whatever, bending that system to your will, but just a little bit. So today I'm going to give you sort of the first complete answer to that. Although it'll only work for fairly simple systems, it's sort of a gold standard that we'll try to approximate with more and more complicated systems throughout the class. Okay, so remember in the case of the simple pendulum, and I'm going to have a torque applied at the base. We thought a lot about it. We ended up drawing the pendulum eyeball, right? The phase portrait, if I plot theta versus theta dot, and I plot the dynamics, which is now in, if I write x dot equals f of xu, x is theta dot, so x dot is theta double dot. And on any point on this is a state x, and the dynamics can be represented with a vector at that state x, right? So we had the dynamics of the pendulum that took this sort of characteristic form and gave us phase portraits like this. They went around in roughly circular looking things inside. There was a key set of trajectories here that we called the homoclinic orbit that went to the unstable fixed point. It was repeated, right? So the challenge for today is to nudge this vector field around a little bit and try to make this the stable fixed point. But you're not allowed to just erase the board and draw a new pendulum over here, because that's not what we do in this class, right? In fact, I mean, so, okay, in the extreme, you might like to say, well, I'm going to do feedback linearization. I'm going to erase the entire board, and I'd like to make a vector field that does this, right? I just want, like, everywhere I go to be pointing there. You can't do that. Like, even with feedback linearization, you can't do that. I want to make sure you get that, right? Because you have control over only one of the elements of that vector directly, right? Theta dot is the other element, so it's still a second order system. I don't get to just erase the entire vector field. You know, if I'm in this location, which is, let's say, this location has got, theta dot is, I don't know, negative 0.5 or something, okay? That means the x component of the vector is going to be here, no matter what your controller is doing. All you get to do with control is change this one, so you can sort of, with arbitrary control, you could bring it to any point on that line, you know, with ridiculous torques, but you can't actually flip it around and go that way. Okay? But still, we're not going to try to do that. We're going to try to do this, you know, try to keep the torques small, and we'll be precise about that. And somehow change this vector field so that that becomes a stable fixed point. That's actually a very subtle, hard problem. Like, just looking at the vector fields and thinking, how would I do that? That's actually a very subtle, hard problem. But so we'll use algorithms that are going to do it for us. Interesting. So we talked about the feedback linearization approach, where you could, for instance, take your original controller. If I applied the controller that was, let's say, torque equals 2 mgl sine theta. So it's exactly the controller that acts like gravity times 2, but it inverts gravity. Okay, if I were to insert that in the equation, it would cancel out the negative mgl sine theta from gravity and add back in a positive mgl sine theta, and therefore make gravity go upside down. Okay. So if I'm just trying to convince you in terms of beauty, or sort of how elegant your solution is, maybe I don't need this. But if you're saying algebraically, I could invert gravity. So how do I stop you from doing that? I say, well, let's say torque is bounded by some small number. Okay. And then you might say, all right, well, I bet if I do this controller, if I saturate my 2 mgl sine theta controller, so I'm going to just take my feedback linearization controller. This is just shorthand saying I'm going to take whatever number comes out of here. If it's greater than 1, I'm going to set it to 1. If it's less than negative 1, I'll set it to negative 1. So I'll just try to do feedback linearization and hit the rails when I can't anymore. Then does that work? Is that a good approach to control? I think you'll find out that what that's going to try to do is it's trying to get up to the upright and you've got some limited torque, it's going to go and get stuck right there and not achieve its goal, right? It's going to think it can go up farther and just doesn't have enough strength to do it. So what do you have to do different? Yeah, right? You have to somehow pump up energy, swing around, and eventually get up there. Pretty subtle. So what does that look like in the vector field? We'll find out. Okay. The cool thing is the way we're going to find out is sort of a numerical optimization way, dynamic programming. You might have seen dynamic programming in many different contexts since it's a broadly useful idea, often in discrete computer science, but there's also a continuous time, continuous state sort of formulation of it that is going to be more useful in this class. And we'll do I'm going to try to actually blend the two during this lecture just to make sure you've seen those connections. But the bigger idea is by bringing in some heavy machinery like dynamic programming, an algorithm that can solve it. Yes, it'll solve the pendulum, but actually it'll be a tool that, with some severe constraints, I can put in many different equations into F, and basically the limitation is going to be if the dimension of X is small enough, and maybe the number of U's I care about is small enough, then I'm going to be able to solve it optimally. Okay? And that's going to be just a super powerful tool in our toolbox, but if you want robots to do backflips, it's not going to be good enough. So we're going to understand this, understand how it works for optimization, to formulate controllers as optimization problems. But then we're going to have to give up on the perfect solution as we get bigger. Okay, so all that is to say that the really big idea here is to formulate control as an optimization. And there's lots of powerful tools for optimization out there, and we're going to use many of them in the class. In some sense, the tool we use today is one of the less standard ones, and so it's a special case of optimization that works well. But let's just make sure we understand the big idea first. So how are we going to use the language of optimization to design a controller? The basic idea is I'd like to watch my robot perform some action, right? And then when I'm done, I want to give it a score. Okay? So if you're given some trajectory, I'll often use this notation with a dot here to say sort of for all t. So if I watch the robot act with some controller, right? At the end of that, I want to I guess the Olympics are on. I want to sort of go up like this and say you got a 9.7 or something like this, right? And so the game becomes, writing down some function that tells me that this was a good thing to do and this was a bad thing to do, right? How do you observe a trajectory and somehow give a score that gets your controller when you optimize this objective to do the right thing? It's kind of funny because there's really two different camps that use all this language and use all this machinery, right? There's the optimal control people, the sort of starting with control theory and systems theory and coming to optimal control. And then there's the reinforcement learning people that are coming from computer science and algorithms and coming towards this same material. And they use different words for exactly the same things, and I'll try to use both of them so you're comfortable with both of them. So there's a couple, sort of humorous differences, right? So reinforcement learning people talk about reward, and optimal control people talk about cost, right? So they don't reward you for doing well, they penalize you for doing badly. Optimal control people generate controllers, and reinforcement learning people give you policies. Same thing, right? So it's easy to map between them, right? Policy is the same as a controller. And then the reinforcement learning people talk about value functions, which we'll talk about, and the control people talk about it typically as cost-to-go functions. But these are basically different words for exactly the same thing. Okay, so our goal then is going to be to find the optimal policy, optimal controller, use this whenever I mean optimal. Put a star up there, okay? So I'm going to find some new function, pi, controller pi, that takes my location and state and decides what torque, or in this case to apply, what control to apply. Okay, so let's, before we do it with an algorithm, let's do it for maybe like the one, there's very few cases where you can actually solve these things in closed form. But it's super useful to do it at least once. So, famous problem, famous solution. The double integrator just means that my dynamics, still second order, are q double dot equals u. The problem becomes interesting if I put limits on u. Okay? If you want to think about this physically, and I always do, then I think a good way to think about it is, if you want this to be F equals ma, so then you have a mass with mass 1, and some force being applied to that mass. So I always think of it as I've got like a brick on a frictionless surface, okay, that someone is pushing with some force u. Okay, and the q is the position on the surface, and maybe our goal could be to drive that to 0. In minimum time. So what does that mean in this sort of configuration? Right. So you're gonna if it's stopped for sure, you better start pushing, right? You push as hard as you possibly can until a critical moment when you have to hit the brakes and brake as hard as you possibly can. And if you do it right, you're gonna come to a stop right there. Okay? So let's see how that plays out. So that's Bangbang Control. It turns out it's often, the result of systems that have minimum time for sure cost functions, but cost functions that don't penalize action, but do have some bounds on the action, is very often comes out to be Bangbang Control. So if you say, I want to achieve some goals in my state space, and I don't care, I'm not going to penalize using torque, I have some torque limit, almost always the right thing to do is to push as hard as you possibly can until you need to brake as hard as you can. So Bangbang Control is sort of a general idea. So what does it look like here? Let's make sure we understand the geometry of it, because we're going to make sure we can recover it with our tools here. So if I have q double dot equals u, let's try to understand the dynamics first. So I guess working back from the end, I want to find out a solution that if I'm braking maximally, I understand where that goes, right? So let's just make sure I understand if I'm slamming on the brakes, what does the system do, right? So if I make any sign errors or anything, please call me on it. Okay, so You know, this is one of the few differential equations I can do on the board here, and it's got the trivial second order solution. What does that look like in phase space? If I plot Q versus Q dot, right? This looks like a parabola. I have to think about how Q dot evolves and Q evolves relative to each other. If I were to start at 0, 0 and apply u equals -1, then I'm going to start getting some velocity, and I'm just going to go off like this. Right? Similarly, if I, yeah?
Sorry, what's the very first symbol of the first line? Something.
This?
Yeah.
I squiggled in a T because I forgot it the first time. That's just Q dot at time T. Yeah? Sure, yeah. And similarly, if I start anywhere here and I apply these are the u equals -1 trajectories. No matter where I start, I'll just start gaining negative velocity and whoosh, head off. The cool thing is if I have positive velocity already, then if I start here, then I'm going to decelerate until I get to some stop, at which point if I continue on, I'll do something like that. And there's a magical place where if I were to do this, I missed. That wasn't the magical place. Move it over a little bit here. Boom. Okay, right? So there's a magical place where u equals -1 ends up, if I were to apply it from that magical place, or any, a set of places actually, that anywhere I apply this u equals -1 and then turn it off when I'm there, I'll arrive exactly at the origin just like I planned. And certainly on that path, there is no faster way to arrive at that origin. Okay, so it's not hard, not a big leap now to say, what are the solutions if u is +1? Those are the other interesting ones, since I know I suspect I will be in Bang Bang. So if I started with +1 here, I'd get these sort of solutions going out, right? And again, on the bottom, if I have negative velocity and I do that, I'm going to decelerate. And there's some magical place, which I'm going to cheat and go back from the origin this time, right? But it went this way, right? There's some magical set of states there where if I were to accelerate from having that velocity, I'll do positive force there and end up stopping exactly at the origin. So what's the fastest way to get to the origin from here? The best I can do is take this, push as fast as I possibly can until I hit this sweet spot right here, and then glide right into the origin. Right? The fastest way to go from here to here is boom. And that's true actually in general. This curve is magical. The best way to do anything here is to get to that curve as fast as I can and then decelerate until I'm there. So if you put all that together, then you can draw the optimal policy. In fact, it's pretty simple. That whole thing boils down to that anywhere over here, I want to do which one? U equals -1? And anywhere over here, that's including, I should make sure this is the right color here. This line is the U equals -1, and then this line is the U equals +1 solution. Right? And that this curve is magical. It's this quadratic that's described by those equations. Okay? and the solutions are ding, 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 ding. But the optimal policy that comes out is actually pretty simple, and it's it's one of the few we'll ever get a complete understanding of. In fact, even proving that this is optimal is sort of annoying. It's like you look at, so why is it annoying? So every theorem you go through, all the standard theorems they're like the sufficiency theorem, for instance, that we write down. It technically assumes that that things are continuous. So this satisfies all the requirements for some of the theorems we'll put up. In terms of, it checks, it does everything you would require, but that theorem doesn't actually technically hold because the system is discontinuous, right? So it's like you get lots of evidence that it's probably correct, it's probably optimal, and it takes a lot of machinery to actually show that it's optimal. So the challenge is, how do I write an algorithm that would have discovered that? And it turns out that graph search is actually a pretty good place to start, okay? So why is that? So any minimum time problems are actually sort of closely related to the shortest distance problem on a graph. And the intuition I want you to have here is that if I were to put a graph, so I'm going to just intermix sort of a very digital concept here of like some discrete graph that I can tile over my state space. And this is only an approximation. It's just for illustration purposes here. Okay. Then, the edges of that graph are going to be the possible control actions. So maybe I could go here, I could go here, I could go here. There's transitions there, but there's no transition, let's say this way. That wasn't possible given my torques. Okay. But given those are possible transitions, and similarly all the way out here, right? There's some possible transitions. It turns out that if I were to just draw in all the feasible transitions and ask what is the shortest path from here to here, the answer is I'd actually have to go up there and come back down, and that's the shortest path. Okay? So the same kind of thing we're doing on Google Maps, to find paths from here to Philly or something, gives us a tool to actually solve these minimum time problems. And there are many ways to solve shortest path problems on the graph. The one that commutes most beautifully with the control is dynamic programming. It's actually impossible. How many people feel like they know what dynamic programming is? How many people feel like they know the graph search version of dynamic programming? How many people feel like they know the continuous time state version of dynamic programming? Yeah, okay. It's hard to do the intersection of those two. So how many people know both already? All right. So that graph I drew on top of the state space, is just one idea. If you give me any graph on the board that has sort of any topology, and there's some edges that connect, I can always ask. Sorry, yeah?
Sorry. Why is the shortest path on the graph necessarily the minimum time path?
So it depends. It's true. So it should be the case though, because the trivial version of this would be a weighted graph with all edges equal to 1. So I think that's right. We're going to see it exactly in the slightly more general form. Is there a reason you doubt it?
Well, because like it's a transition in space or in velocity that doesn't seem to be equivalent to a transition in time.
What if you waited where the distance between each point is the time it takes to transition between them from the shortest path becomes the shortest time travel?
Good. So I see. You're worried about the discretization, the effects of.
Like if you're going really fast, it takes a lot less time to move between different locations.
So that would be, so okay, I'm brushing the details of the discretization under there because in fact it might be that with u equals 1 or -1 I don't actually end at any node, right? If I've discretized, so that's the first observation, is that every one of those arrows is a lie, but it's approximate and it's reasonable. And then the second question is, so if I'm at a high velocity state, for instance, I might actually jump a fairly far distance to connect to the nodes that are closest to where my arrow would have landed, right? So the geometric distance in that picture is not necessarily the connectivity of the graph, right? So there's some long vectors at the high velocities that are going to go, farther over, and so you can go, across more distance in one step with a cost of 1 when you have high velocity. Yeah? That's great. That's a great question. The one that I always hate brushing under the rug is the fact that it doesn't land in that node, but we're going to, so I'm going to get around that in the numerical examples today by using function approximation, to using an approximation there, a mesh sort of approximation, but I'm going to leave the details of that until we get a little further. Okay, so in general, how do I think about problems like this? So I want to be very, because of this subtlety between continuous state and continuous action, I want to be very sort of distinct with my notation. So I'm going to say that my states are, instead of x, I'll use s if they're discrete, and a instead of u. Okay, so my dynamics, in some sense, of my graph is my connectivity pattern of my graph, but I could still write that as some sort of dynamics the way we like to think about it. It's just a discrete dynamics, which is some function that takes me from my current state. If I take some current action, it takes me to a new state, right? So this might be the transition. If I say action equals 1, this might be action equals 2, okay? And so I can write it in almost the same notation, except for the very discrete change that I made there, right? Now, the shortest path has a couple different algorithms that can solve it, given that formulation. But let's just even also think about a generalization of this. So the shortest path is where the cost of all of these is, the transition is the same. I get a cost of 1 every time I take any one of these edges, and then I would measure the total distance just counting edges. But there's an obvious generalization of that where I could put different amounts of cost on different transitions and then ask for the weighted shortest graph problem, right? So and the notation I want to use for those weights is that I'm going to use a cost function, which I'll write as g of s a. It's the cost incurred from being in state s and taking action a. And it's just the labels of the weights that I put here. So I can perfectly take that and write it down as a function g of sa. That's magical in terms of possible cost functions that I could write. Why is that magical? So I told you, the very first thing I said was we're going to take trajectories of our system and then assign a cost to them, right? So I could have instead said, you give me an entire path through the graph, and I'll put up a score, right? This is actually saying, well, no, hold on. I'm going to restrict the class of possible scores I could give you to ones that are assigned additively across as I traverse the graph, right? So this is implies additive cost, and that's a big, big deal. So my total cost of taking a path, my total score, if I were to start in state S, let's say, and take some set of actions here, if I have, let's say, a trajectory SA now, my total score is going to be the sum over all of the n equals 0 to whatever time horizon I've chosen. So certainly I can go this way. If I've labeled the edges here, I can add them up to find the total path. But this is a restriction on the type of scores you can give me. I'm saying it has to fit this additive cost formulation. Okay? Now, the minimum time problem can fit this, right? So it doesn't feel like minimum time should fit this. But if I were to just say g of SA equals 0 if S is my goal, and 1 otherwise, then you can still write it in an additive time formulation. Right? So if I just accrue cost everywhere until I get to the goal, then it fits this additive cost formulation. Okay, so you can imagine a bunch of different tools for now, given this weighted shortest path problem, how do you solve the, how do you find the policy that's going to be tells me whenever I'm in this state, I should take this branch or this branch, right? The most important one is, so you can, if you're just solving it once, there are algorithms that will traverse depth first or breadth first or A star or all these other graph search algorithms you might have encountered. But if my goal in the end is actually to know what the optimal action to take is for every possible state, if I want to output a controller that tells me what I should do everywhere, then the best way to do it is to actually start at the goal and then work back and compute this magical quantity called the cost to go, which tells me everything I need to know about the problem. And that's the dynamic programming approach. Okay, so the toy problem that you see in let's say a reinforcement learning discrete time, discrete state, discrete action sort of book would be the grid world example. It's a graph that has a robot in it, right? It's like the way you can blend these two, right? So I've got a little robot that lives in a grid. I've got a goal somewhere in that grid, and my robot could start anywhere, and I'd like to find the shortest path to the goal. Now, side note, I actually spent a long time one year making little animations that had sprites of robots dancing to the goal, but I bet on the wrong technology. It's all in shockwave. And so, the Adobe Apple Wars or whatever killed it, I don't know. So you can't actually run Shockwave anymore, but if you happen to have a Shockwave browser, let me know, and Shockwave plugin for your browser, I'll send you the videos. Okay, so today it's not going to be sprites. It'll be like vectors. Okay, so the cool thing that you could do here is you try to compute the cost to go, which you can imagine being, 1 here, 2 for all these states here. So I didn't actually define my dynamics here. So I have discrete actions, which are going to be just or do nothing, right? So up, down, left, right, or do nothing. And my state, of course, is anywhere in the graph. If I have those actions, then I know, and my cost is minimum time, so I get a 1 for every state until I'm in the goal, then I know that I could get here achieving a cost of 1 and then accrue 0 for the rest of time. I can get here by multiple approaches, accruing a total cost of 2, 3, and so on. Okay, so how do I get that out of a graph search algorithm? It turns out the key is to write down this total cost to go. We'll call it J. J star is the optimal cost to go. And we'll say in the discrete case, J star is actually going to be a vector where the ith element of the vector is, if I started in state Si. We already defined it to be J star of I is going to be the the minimum over all the actions I take into the future of my sum of my So I get to make some set of decisions over time. That's my decision variables is, I'm going to take some sequence of actions. Every time I do, for any sequence of actions, I can tell you what the total cost is going to be, right? By saying S0 is my state that I started at, and then subject to the dynamics that I wrote down before, right? Is that clear? The magic now of having restricted ourselves to the additive form is that although the search over this seems kind of scary and hard, it's a vector. I don't even actually know how long it is. I don't know how many decision variables to write there. How do I optimize over some really long-term decision making? The magic of the additive form is that I can also write this recursively as the minimum over an immediate action A of taking that action immediately. I get a one-step cost, and then I get the cost to go, optimal cost to go, of wherever I landed. So my index was on the subscript here, so I'm going to write it like this, okay? So this is a long-term optimization, but if I started to solve for J, then I can reduce it to a one-step optimization, which says I'm going to incur one step of cost, and then the rest of the cost I should expect to achieve over time, incur over time. That's again optimal control versus reinforcement learning, right? Is just J star f of SA. I'm trying to be very careful with this notation, so I think the details should be right. If they're not, call me on it, and if you have questions, call me on it. Okay, so this is a recursion which defines, if J star is in fact the optimal cost to go, then it should satisfy this equation. Right? That's a property of the optimal solution J star. The amazing thing, which is sort of a screw case in the optimization world in my mind, like there's a couple places where we have general tools for optimization, and then there's a couple things out there that just have special case solutions that are magical and good. Like SVD is just magical, right? It just doesn't really fit in the rest of the optimization world. And so, somehow value iteration, which is what this is, it has these magical properties, and it's just magical and good. Okay, so if I now take this and think of it as an algorithm, what do I mean by that? If I have an approximation of J, and I compute this value here, and I minimize over A, and then I write that value into a new approximation of J, then that's an algorithm, and it has shockingly strong convergence properties, okay? Like it basically, you can do almost anything to it and it still converges. So because this is thinking about value functions or cost to go functions, this is typically called the value iteration algorithm. So now I really say I have some estimate J hat of the optimal cost to go. It has some, it's a vector. It has an ith element. And I'm going to, in my updates, I'm going to run through and say for all I, right into this new value J hat is I always use that for estimate. The min over A, G, S A plus J star F S A, like this. And this is, I only have available as my estimate. It turns out this has got shocking convergence properties, okay? Yeah, it's strong convergence. Okay, so if I were to start J, if I just initialize J hat to be 0 everywhere, okay? Then on the first step of the algorithm, I'm going to just get the one-step costs.
So what sort of problems or situations would it be difficult for value iteration to converge?
I think we're going to show good examples of that, but there's a couple different ways to answer that. Let me answer it in just a second, but I'll try to give you a good answer to that. So first, the times it does converge nicely is, if I start this at 0, for instance, it will actually propagate through and end up at the optimal J star. I could also even there's a distributed version of value iteration. I don't have to do this in order. I can sort of pick which index I want to update at random and just update one of the elements of I. Okay, I have to pick all of the elements eventually with infinitely often, right? I can't ignore some states. But if you do a distributed version of this algorithm and update the J's sort of randomly, then that'll still converge. It converges from any initial J hat to the optimal J star in the discrete time, discrete state case. Okay, so it's really strong convergence properties, and moreover, it reveals the optimal, if you have this, it reveals the optimal policy. Because the optimal policy, pi I star, right, which is the action you should take from state Si, is just the A that minimized that term. Argmin over A, G of SA. Sorry that the board isn't getting erased as well as I'd like. If I know what the cost to go is everywhere on the board, okay, if I figured out I got 3s here, 4s here, I don't have to look all the way at the goal to make a decision. All I have to look is one step there might be some action cost to go here, here, or here, I assign them all the same. So I get to go look at my neighbors. This one is 5. So I want to minimize in one step my cost of taking the action plus my cost to go for the rest of the steps. So I know here that this actually or this would be optimal. And I don't have to solve the whole, I've reduced it to a short one-step problem. Yeah? Now there's a couple interesting things here. So the optimal cost to go is unique, but the optimal policy is not necessarily unique. Right? This one, you could have chosen either of those two actions, and they're still both optimal. Okay, so when would that not converge? You can write bad cost functions, right? So, or you can formulate bad problems. If I were to surround my goal by a pit of despair, right, in which no robot can ever traverse, right, then it will accrue cost forever and will never be able to get to the Shambhala, where it achieves 0 cost for the rest of time. So what happens in that case is that the cost will just continue to increase forever and ever. The total cost to go is unbounded. So this algorithm will never terminate. It'll just get bigger and bigger and bigger. Okay, now that's a ridiculous case. You probably won't do that on accident. But imagine, remember I told you there's some subtle things about, let's say, stable in the sense of Lyapunov versus asymptotically stable versus whatever. Imagine you have a system, and they certainly exist, that it's possible to stabilize in the sense of Lyapunov, but it's not possible to stabilize asymptotically. And you write a cost function that requires you to get to the origin in order to stop accruing cost. That is an ill-posed problem. It doesn't have a good solution, because you will never be able to drive the thing to 0. It happens all the time, actually. If you have noise in your system, let's say you have any sort of random disturbances, process noise in your system, okay, then even if you get to 0, you might get bumped away or something like this. And in fact, if you integrate cost over time, you will accrue infinite cost. So you have to handle that case pretty specifically. Okay, there's a special trick for linear Gaussian systems, but actually, the cost to go of a linear Gaussian system is infinite. Okay, it still has a closed form solution, but that's it's a detail. It's a trick. Okay, so I don't have all of the animations handy, but I saved one. It's actually not even the one with the robot sprite, but. Yeah. I found some, obscure SWF visualizer hours ago. All right. I put a pit of despair in here for giggles, okay? And this is the value iteration algorithm running. I don't even know the controls on this, but. Okay, so. Okay, so the robot has a goal here. It has a cost. Well, you can tell it's taken a few steps of the algorithm already. Where is the cost high? So I basically defined an obstacle here by saying if I'm in that state, I'm going to incur some large cost. Okay. So how many states did I assign high cost to? Can you tell from looking at this intermediate solution? 10. 10, whatever, 12 maybe? Something. Right? Because it takes 2 steps to get out of the pit of despair from the middle. Okay, so you get higher cost if you started in the middle of the pit, but you still get a lot of cost if you start on the edge. So that whole yellow and red region is an obstacle. Okay, And you see every iteration of the algorithm. I started it at 0. The total cost everywhere is almost 0. Okay? After one iteration of the algorithm, the cost everywhere is 1, except for the places where it knows how to get to the, well, it turns out it's going to be 1 everywhere, right? So first it's going to go through and it's going to write 1s everywhere, basically. The second iteration of the algorithm, I'm updating the entire vector at a time in batch. It's going to figure out that those get to stay at 1, but these get 2s, and everywhere else is going to assume it's going to get at least 2. And then as it goes out, it's going to solve for the 3s, it's going to solve for the 4s, it's going to solve for the 5s, all the way out, right? And at the same time, it's drawing the optimal policy, or one of the optimal policies. Now, it looks like that's going to change the solution over there, but that's just because the axis, the color bar changed. So it didn't actually change the optimal cost to go over here at all at the end. Okay, and it eventually moves out and covers the space. Okay? Simple optimization, simple graph search, applied to a grid world. If you have a robot that lives on a chessboard, you're done. But what I want to convince you now is that this algorithm, when I apply it roughly like that, modulo, I'm going to sweep the details of the not landing exactly in the circle under the rug today, and we'll get to them later, is going to have penetrating insight into the dynamics of our systems. Okay? This is going to solve the hard problems that I don't really know how to do in my head of the vector fields. That's simple machinery, okay? Now I spent basically every hour that my kids were asleep since Thursday making sure that you could run this in Python, because I had it all in MATLAB before. So it should work. There's a couple little quirks that I'll resolve before I push to you guys tonight. But let's do the double integrator first. Okay. Here's value iteration for the minimum time problem on the double integrator. Let me make that a little bit bigger. I'm now thinking of it as a mesh approximation to the continuous dynamics, and I've got transitions from the edges of the mesh that are very much like this. Okay? And you can see the code, there's no mysteries. Okay, I also wrote it on a faster machine than this, so I would have just displayed less often if I had known how slow this was going to be, but that's okay. It's fun to watch still. Okay, so this is Q on this axis, Q dot. If I look down from the top, this is the cost to go. Okay. What do you see? You see that there's low cost if I'm in that quadrant, right? If I'm in the if I'm positive velocity moving towards the goal, then I've got lower cost than if I'm positive velocity and moving away from the goal. That seems consistent. One of the quirks is that the policy disappears on the last frame, which is awesome. That'll be resolved tonight. It's a one-line fix, but it would involve me building again, and I didn't have enough time to build it. All right, so now let's watch the... So there's junk because there's arbitrariness in the optimal policy before it starts. This is the optimal policy plotted over that same. Okay. And what does it find? Finds that policy right there. Yeah? Almost. It's actually, we'll ask you to look at some of the details of the numerical discretization in the problem set. It's not just that it's like a staircase version of the optimal switching surface. The optimal switching surface is actually in the wrong place, and you'll have to understand why. It's for subtle reasons, but it's cool. Okay, so that's good, right? It discovered what I consider to be a pretty non-trivial solution, but for a trivial system, one that we could solve analytically. It roughly solved. the cool thing is it can solve pretty much any low-dimensional system, right? So, well, I could have changed the cost function. If you have a quadratic cost, that's actually worth doing that real quick. So if I were to, instead of having a cost that was one or one everywhere except for 0 when I'm in the goal, that's actually, so those policies are not things you typically want to run on a real robot, just saying. So like if you have a humanoid robot, for instance, in your lab, and you walked up and tried to run that controller, we would all yell at you because that's going to be, well, no actuator is going to be able to execute that, but in general, these things are going to be bad. They're going to be, if there's any errors in your estimate of what state you're in or whatever, they can chatter, and there's lots of reasons why you don't want that. So typically, you make controllers a little gentler for your robot by putting a little bit of penalty on the U, saying, all right, all things equal, let's try to keep the torques low, guys. And so a standard way to do that would be a quadratic cost on U. So if you add in, so a standard quadratic regulator cost would be, I'm going to write it in the continuous form because it makes more sense, would be something like X transpose X plus U transpose U. And in general, you can weight these differently, and we'll see it with some weighting matrix often in the class here. Okay, but something that says, all things equal, I like being at 0, but be gentle getting there. And if I make this 10 times this, then it'll tell me to be a little bit more gentle. And if I made this 10 times bigger than that, then it would be more aggressive in getting there. Okay, this would be a smoother version of the same problem. And the result is revealing, I think, okay? First of all, we know that the optimal solution to that for the double integrator should be a linear function and a quadratic cost. So I like to show this because it reveals the limitations of the numerical approximation. I've only discretized a finite set of state. So there are some boundary effects where my discretization, the optimization doesn't realize that if it goes off here, it doesn't understand the dynamics of the edges very well. It pushes them back to the edge as well as possible. And similarly here, there's still some limits. There's a discretization in the inputs, and there's a limit on the input that I'm searching over some discrete actions. Okay, so it's close to perfect. This should be a quadratic function, and it comes out to something that looks very quadratic, except for at the edges, and this should be linear, but it doesn't even draw the final frame, so who knows? But it will tonight. All right, now, the big reveal.
Or in the Q.Q diagram, if you have a quadratic regulator, does it look the same or is there a change?
Ah, okay. What does the resulting controller look like?
Yeah.
So it's basically a line that looks like this. So that's that's the thing that disappeared in the last frame. But this one looks like a staircase, right? Where it's 1 here, -1 over here. The other one is just a smooth line like this. So it lives on the plane. If the saturations are still there, it changes that a little bit. But if there's no saturations, it's perfectly aligned. Okay. Here's the pendulum. Same exact algorithm. Now we're just going to stick in F from the equations of motion of the pendulum, mgl sine theta, okay? Look what it does. Okay, it looks pretty. Anybody see the eyeball? There's nothing about the algorithm that knows, I didn't type in eyeballs, right? I typed in f equals a. I typed in an eyeball that was sort of in the other place, right? The passive pendulum has an eyeball like this, okay? But the stabilized pendulum has now an eyeball, a low cost to go up by the upright equilibrium, okay? So this is the upright here. And then it has low cost when you're close, and low cost, of course, when you're coming towards the upright equilibrium. You have low cost along this axis, okay? And then we get the wrapping effects right and everything like this. This time it wraps over from here over to here, and it gives you this sort of beautiful physical, understanding. This graph search algorithm, I think, just penetrated the dynamics of my pendulum in a really nice way. The policy is pretty subtle, right? So would you have thought that was the policy you'd want? Right? Well, what do you see? When I see that, I see, okay, it's saturating all over the place. It's not a very smooth version of the policy. So that immediately makes me want to see what happens if I were to, for instance, what if I were to make U 10 times more expensive? Okay. See if I can keep it away from those saturation effects. That's better. Now it's also got the staircase thing going on because I've discretized action space. We'll work on getting rid of that. I'll show you how to get rid of that on Thursday. Okay. But man, I feel like this is totally non-trivial understanding of the nonlinear dynamics. I would say this is the reason that I, started really believing that for any significant control problem, it's going to be the algorithms that are going to get us. We're not going to wait for a theoretician to find that function. Right? It doesn't take just like a pendulum to convince me, right? Which you might. It's not obvious. It's beautiful. Okay. What do you think the minimum time problem is going to look like? It's interesting, right? Because it depends on what the torque limits are, right? You can make it harder or easier. If my torque limits are very, very large, it looks like that. If my torque limits are very, very small, it could take an awful lot of pumps to get up there, right? So at some point, you're going to fight against the resolution of your discretization. I picked something in between, but hopefully with an impressive number of pumps. Let's see how the simulation playback speed I set. It's like back when I don't know if you guys are probably too young, but I used to have, we used to have computers that if you, that basically, you'd get a new version of the computer and suddenly your character would run 4 times as fast as it's supposed to because you went from a 386 to a 486. I think I went the other way just now here, so we'll see. All right, this is the minimum time problem for the pendulum. So I would expect the controller to be bang bang. Okay, it takes some time for that solution to sort of propagate because it doesn't realize that it can make it all the way around, but it does. And it'll find the eyeball again, okay? And, slowly work this out. And this policy doesn't look ridiculously complicated, but I think I had it running a little sim at the end here. This policy, when executed, pumps up like 5 or 6 times. In that. Right? It lines up in just this magical way on the state space. Sorry for the last minute computer swap, changing my timing. It's all plotting, by the way.
Can you explain how you conceive that it swings up 5 times?
I can't. It's shocking to me that it does. It's only by simulating the solutions that I can see that the crevices it chooses to follow through that are, they wrap around on itself, land in a different place, end up pumping and pumping and pumping to do that. I'll show you. I mean, there is a simple controller that can achieve that. That makes it less surprising that a simple thing like this could achieve it. A simple controller that we'll use as a baseline later is if we just look at the velocity I'm currently going and apply torque in the same direction as that velocity, then that'll always add energy. That's not so good when you get to the top. You got to do something different. But if you just want to pump up energy, there is a simple nonlinear controller that could do it. I worked really hard on the animation. I'm going to make you see it. Just have to turn down the plotting. This is doing exactly the same thing, I just plotting 5 times less often. Yeah?
So, I asked, why does it bump 5 times and how do we shape the plot? That's pretty question. Interact.
All right, here we go. Oh, it's like half real time. Okay, but still. It's going to pump, it's going to pump. Thank you for interrupting yourself for this. I'd be really sad if it doesn't make it, but I think it will. It should. See? It's good. I mean, that is like really, in my mind, that's a very deep understanding of the sine function, basically. Oh, it's going to get there. Come on. No faith. All right, sorry.
So it's already hard to tell whether it would run 5 times or 4 times. What about the even harder question of if we were to actually build it?
Yeah?
Would it tear itself apart?
Would it tear itself apart, right? So there are answers to those types of questions, right? So typically they involve injecting into your cost function something that captures the thing you're worried about, right? So I can give guarantees. This version, because of my discretization, I don't have strict guarantees about the continuous system. I could have run that and it would have just gotten stuck somewhere because the discretization was too coarse or something. But there are versions that will do that are better, that are more continuous, that can give guarantees. And the type of property you might want is something like guaranteed cost control, saying like even no matter what happens within some bound, I'm guaranteed that my performance will not surpass my cost that I will receive will never surpass some amount. And you could put in, if you have then in your cost function something like exploding is bad, or falling apart, running into walls is bad. If you can solve that problem, which you can't always, then you should have some sort of guarantees in the real world. And that is the game, and that is roughly the stuff of a robust control, is how do you put in the known unknowns, if you will. You try to put in things you suspect about your system, but you don't have quantities for it, and you try to say, for all of the things that might have happened in that, I'd still like to have some bound on my total performance. And that's a more complicated version of this, but it fits into this type of framework. The unknown unknowns are the hard ones, right? If you like, I didn't realize that could happen, I didn't write it in my equations, I didn't give my controller a chance to handle that, those are tough.
What about when your state estimation is perfect?
Yeah, so that is the biggest problem with this. There's an answer that you probably the thing that almost everybody does, because these tools are so good, is you do state estimation to try to estimate your x, and then you run these controllers, and then you try to maybe do a couple things to make this controller robust to the fact that x might not be perfect. I actually think that's fundamentally wrong. I mean, everybody knows that that's not an optimal thing to do in the nonlinear context. But even the very notion of what is x, what is the dimension of my state, I think is in question. If I start manipulating, if I'm folding laundry or something, right? What is the state of my shirt? And do I have to know it completely in order to decide my next action? Probably not. So the only thing I don't like about these approaches is that they're state feedback, that they require you to be a function of the state of the world. And I think in many cases it's too much to ask to know the full state of the world in order to make a decision. And that's something we'll talk more about later too, although I don't have all the answers on that. That's still sort of open problems. Any other questions? Okay, cool. So you get to run this and tonight after I commit, and play with things, change the cost function, get some physical intuition. This is the best chance you have for getting mechanical understanding of optimal control, because it gets more complicated after this.